Okay, welcome to class. Today we're going to talk about temperature and specific heat. This is more of our discussion of thermodynamics. So let's start with temperature. If you were here a couple days ago, if you weren't taking the exam, you already know about this, but in a short, temperature is the unit by which we measure average kinetic energy of the molecules in a sample of a material. So all the time, molecules in a material are bouncing around, they're bouncing off of things, they're moving. When we say absolute zero, you've heard of that before. If we have zero temperature, that means we have no kinetic energy of molecules at all. Turns out that this is impossible. But in general, temperature is that measure of average kinetic energy. We have units of Fahrenheit, Celsius, and Kelvin. Kelvin is the most widely accepted for science because it starts at absolute zero. It is an absolute scale. It uses the same increments as Celsius, but it starts at zero, which is absolute zero, whereas Celsius, its zero is the freezing point of water. Its scale is the same, so 1 Kelvin is the same difference in temperature as 1 degree Celsius. There are no degrees Kelvin. That's not a thing. It's just Kelvin. Okay, this object is 200 Kelvin, not degrees Kelvin. So temperature and heat are not the same thing for the physics world. Temperature is a measure of kinetic energy, and then heat is the transfer of energy. And we'll see more of that in a minute. So temperature doesn't mean anything if it's not stable across a material. So if you have a transfer of heat happening, okay, there might be a temperature differential, so a difference in kinetic energy throughout the sample. So if we want to measure a temperature, we want to say that a sample or an object is a temperature, it has to be at thermal equilibrium, meaning the whole sample has the same temperature. So when we have two objects, two bodies or samples that are in contact with one another, they will move towards a stable, identical temperature. We talked about entropy yesterday. This is an entropic process. That's how we say it. It is more statistically likely for that kinetic energy to be spread out over the whole of the two objects that are touching, as opposed to all of the temperature, all of the kinetic energy staying in one. Okay, that would be equivalent to the free compression of all the air if, when these two objects were touching each other, all of the kinetic energy stayed in one of the objects. So entropy says that that energy will spread itself out. So they'll move, if they're different temperatures and they come into contact, they will move towards a stable temperature in between the two individual ones. You have one at 0, you have one at 30, they will move somewhere in between. However, the actual temperature that you reach will depend on the heat capacities of the objects. It's not as simple as taking an average of the two temperatures. These two objects are going to have different properties that are going to dictate the flow of energy between the two and the amount of temperature you end up with. So what is heat? When we say we're transmitting temperature, okay, we're transmitting kinetic energy of molecules. So if I take one hot thing and put it up against one cold thing, the molecules in the hot thing, okay, that has a higher temperature, they have more kinetic energy, so they're bumping up against stuff. So when you put it into contact with something with lower kinetic energy, those molecules keep bumping up into the molecules of the lower temperature object and exciting them and giving those molecules more kinetic energy. So what this is heat. When we say heat in physics, what we mean is the transmission of energy. So when we say something has heat, that is not correct physics language. Okay, you do not have heat, you transmit heat. Just like temperature only has a meaningful use when it's stable, heat only has a meaningful context when it is transmission of energy. And because it's energy, heat is in joules, which is the unit of energy. A calorie in food is a unit of energy. It is a certain number of joules. So when you eat a certain amount of food that has a certain number of calories, that is also energy. So heat as an entropic process, so through entropy, heat will spontaneously move from higher temperature to lower temperature. Okay, so entropy says that the kinetic energy will move from the more excited state to the lower excited state. It will spread out. You will not get heat being sucked out of a colder object. Okay, again, cold is not really a good physics word, so heat, kinetic energy, will not move from the lower temperature object to the higher temperature object unless you pump a bunch of energy in, okay? Yes, you can, right? A refrigerator is an example of this. We have a lower temperature refrigerator that continuously pumps heat out of it. However, we have to use energy to do that. So obviously, if we unplug the fridge and we open the door, naturally, through entropy, that kinetic energy of the room will radiate into the refrigerator and they will come to thermal equilibrium, the same temperature. So this is a kind of a microscopic picture here. We can see that in our coffee mug, if we look at the, here is our coffee itself, and this is the wall of the mug, and here's the air. So we can see that we have a lot of kinetic energy happening. These hot or higher temperature coffee molecules, mostly water, are moving around with a lot of kinetic energy, and they are smashing into the wall. You know, you have, they're going in all different directions, but this one right here is coming into collision with the wall. This one's going to hit the wall, that one's going to hit the wall, etc. So the wall of the mug is made of a ceramic. Okay, when this one hits, it's going to move this molecule, which is going to move this one, and this one, and this one, and this one. And eventually, this outside one is going to excite a molecule of air, okay, and that's going to shoot off and have more kinetic energy than it did before, okay? So the transmission of energy is what allows things to come to thermal equilibrium. What we want when we say we're insulating something is we want a wall that is very bad at transmitting energy. Okay, we want something that is very, very bad at transmitting that energy. That is a good insulator. Glass is a great thermal insulator because it does not want to transmit this energy. The bonds between the molecules in the glass don't want that to happen. Okay, so again, thermal equilibrium, they will exchange energy as heat until they reach the same temperature, and therefore the average kinetic energy of the molecules will be the same. And again, to summarize, temperature is a measure of the average kinetic energy. You can have temperature. It's something that you have. Heat is transfer of kinetic energy. You do not have heat. You transfer heat. So, like I said, when we're going to thermal equilibrium between two different types of materials, okay, all other variables being the same, the greater the temperature difference between the two, the greater the rate of heat exchange will be, okay? So, if I have a 1 degree difference between two objects, the rate of heat transfer is going to be rather slow. But if I take two objects that have a 1,000 degree difference, okay, 1,000 Kelvin difference between them, or degrees Celsius, doesn't matter, 1,000 Kelvin difference between the two, those are going to exchange heat very, very quickly, okay? And we can kind of see this in that a very, very hot bowl of soup, okay? It cools off from boiling hot to palatable relatively quickly, and then it takes longer for it to go from a decent eatable temperature down to room temperature. So the greater the difference, the faster it's going to be. And again, regardless of the absolute temperature, this is going to happen. All that matters is the difference. So the rate of change, rate of transfer between 30 degrees and 35 degrees, okay, that delta T is 5 degrees, okay. That's the same as 1,000 and 1,005. It's still only a 5-degree difference. So the rate of heat transfer between these two situations is going to be exactly the same. So now let's talk about specific heat. So specific heat capacity is a property of an object, a property of a material. It has to do with the structure of the material itself. So all materials do not accept heat in the same way. If you were here 2 days ago, you saw the diagram of the different molecules. So if we have a molecule that is monoatomic, meaning it's just a particle, it has energy and motion to go, laterally, linearly, linear motion. However, if we have some molecule, some triatomic molecule, let's say, okay, it can vibrate back and forth with these bonds. It can vibrate. It can rotate. Okay, it can rotate back and forth, and it can spin on its other axis. And so there's all other kinds of places to put that energy. And that was why you have a difference. So given a certain amount of energy via heat, different materials will have different changes in temperature. If I pump 50 joules of energy into water, it is going to have a different change in temperature than if I take the same 50 joules of energy and pump it into glass. Okay, so if I pump 50 joules of energy into water, let's say it has a change in temperature of 5 Kelvin. If I pump the same 50 joules of energy into glass, it might only have a change in temperature of 1 Kelvin, and that is due to the structure of the material itself. And that number, so there is a number that we can associate with this, and that is called specific heat capacity. So this is the definition. So the number itself of specific heat capacity is the amount of energy required to change the temperature of 1 kilo of a material by 1 degree Celsius. Okay, that is the definition. That's how it's calculated. If we had 1 kilo of this material and we wanted to change it by 1 degree Celsius, how much energy would we have to use? Technically, there's two different types of specific heat capacity. This has to do with more complicated thermodynamics. You can have isovolumetric and isobaric, but that's another talk for another day. CP is what we call the first. It is heat added at a constant pressure. And CV is heat added at a constant volume. So CV would be if we had a fixed container, whereas we filled a box that was incompressible or inexpandable. However, what we're going to do today with the calorimeters is constant pressure. That means constant air pressure around it, so it can expand volumetrically. Okay, what's our little formula for this right here? Okay, the specific heat capacity is Q, which is the heat added to the material, divided by the mass of the sample and the change in temperature of the sample. So we can see if mass is 1 and change in temperature is 1, right? 1 kilo by 1 degree Celsius, then CP equals Q. So it's the same, it works out. Again, change in temperature is what matters, not absolute temperature. So there are some common specific heat capacities. Water has a very high specific heat capacity, meaning that it takes a lot of energy to change the temperature of water. Hydrogen has a crazy high one, and we can see that the metals over here, metals have relatively lower specific heat capacities. It takes less energy to heat up a metal to the same temperature as it would, let's say, water, seawater, etc. So how do you figure out this specific heat capacity? Because it is a useful thing to know. Okay, that is called calorimetry. A calorie, again, is a measure of energy. This is actually how they figure out these exact calories of a particular food. You burn it and you see how much the temperature of a certain volume of water changes. That's not what we're going to do today, but that is how you figure out how many calories a sample of food has. So what we're going to use is we're going to use water. So we're going to say that if the specific heat of water is known, which it is, we can use water to help us find the specific heat capacity of another material. We can equate these things. This is a calorimeter. Okay, we have 3 that I have set up for you, but this is how it works. You have basically it's a cup within a cup. This is an insulator. This is an insulator, so for us it's going to be styrofoam, which is a decent insulator. So what you do is you fill it with a certain amount of water. Okay, you're going to have to mass that water to figure out how much water you have. Okay, and then you take a sample of the material at a different temperature. You put it in the water, you seal it up so it's nice and insulated, and then you measure the change in temperature. And there's a nice formula that can help you figure out the specific heat capacity. Because when you put this object at a different temperature than the water that it is in, okay, eventually they will come to thermal equilibrium. So if the sample, let's say the sample is really, really, really warm, warm, it has a really high temperature. See, it's hard for even me to break out of the common parlance. So let's say it has a very high temperature compared to the water, okay? This will lose heat. It will transfer heat into the water until they come to thermal equilibrium. And if we measure how much, so say we start off, here, and then our thermometer tells us that our water had its temperature increased, however much this would be, then we can have a useful handy-dandy formula that's going to tell us what the specific heat of that sample is. How much temperature did it give, how much heat did it transfer to the water? What are we going to do? Okay, we are going to heat our sample of material up to 100 degrees Celsius. We're going to put in water, which is going to be at room temperature or some temperature close to room temperature, allow them to come to thermal equilibrium, and then we're going to measure the change in temperature of water with the thermometer. This is what we need to know. So, because of conservation of energy, the amount of heat that is transferred into the water is the same as the energy transferred out of the sample. So if we start with C equals Q over M delta T, if we set it so that Q equals Q, where this is heat and this is heat, so energy is energy, okay, our transfer of energy out of one must equal the transfer of energy into the other, then we end up with this formula right here. So the specific heat capacity of water multiplied by the mass of the sample of water multiplied by the change in temperature of the water from beginning to final is equal to the specific heat capacity of the sample times the mass of the sample times the change in temperature of the sample. Okay, if we know this, 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 and this, we can calculate this. So what are we going to do? We're going to use this calorimeter. Okay, we have a cork here. That is where your thermometer is going to go into. We have a cap. Okay, you're going to pop that off, and that is where you're going to drop your sample into and then cover it up again. And this is a stirrer. So you're going to ever so often want to stir the water up so that there is not a temperature differential across it. This is the thermometer that we're going to use. Okay, here is the probe, the end. It has a little rubber around it and a little conductive metal tip right there. That is going to go into the water in the calorimeter. You have to make sure that it is submerged. Okay, otherwise that means nothing. All right, and I mean, just a power button could not be simpler. Just basically display the temperature on the screen. Okay, if you were here on Tuesday, you saw me use these. They're great, very accurate. Okay, we have beakers. I've set them up. We have a large beaker that you are going to fill with a certain amount of water, at least enough water to cover your ball bearing. You are going to boil this water with the ball bearing in it. If you let it boil for a couple of minutes, you can ensure that the ball bearing comes to thermal equilibrium with... No, and there's announcements. Whoops. Okay, so if you're boiling the water with the ball bearing in it, you can ensure that the ball bearing comes into thermal equilibrium with the water, which we know if water is boiling, it is at 100 degrees Celsius. You can still measure it with your thermometer if you really want to for a more accurate reading. Okay, we have these hot plates. Those are set up as well. Be super crazy careful with these. Okay, this one, in order to boil the water, you're going to have to turn it all the way up. This one, absolutely not. This hot plate can go up to 300 degrees Celsius. Under no circumstances should you go up to 300 degrees Celsius, okay? You should have it up to 100 degrees Celsius and maybe a little bit past that if the water is not boiling. You need to be extremely careful. You have to wear gloves and goggles while handling these, okay? You have ball bearings. I have actually already placed them next to your experimental station. These are about 1/2-inch ball bearings. You have these tongs. These are what you are going to use to take the ball bearing out of the water and put it into the calorimeter. It fits nicely in these little clamps here. Okay, you're going to have to squeeze it from these. When you are using these clamps to pull the ball bearing out of the water, you absolutely must use gloves. The steam will burn your hands. Goggles and gloves, no picture because I'm lazy. Wear goggles, wear gloves. You absolutely must wear gloves and goggles when you are handling the hot objects. All right, what are we going to do? We're going to set up our calorimeter with the thermocouple, that is the end of the thermometer with the little rubber on it, through the cork hole. Fill it with water. You're going to have to mass the water that is in the inner cup. Okay, there's a scale over on the far side of the room next to the whole mess of motion cart stuff that I have. Okay, set up the large beaker on the hot plate with ball bearing. That should not say 60 degrees Celsius. That should say 100 degrees Celsius, aka boiling. Take the temperature of the water inside the calorimeter. You're going to record that on your worksheet. Transfer the boiling hot ball bearing to the calorimeter. Leave the thermometer in the calorimeter and wait for it to come to thermal equilibrium. This should take at most 10 minutes, probably not that long. I have tested this. It seems to be at least 5 minutes. So you're going to calculate the difference in temperature to find the specific heat capacity of the ball bearing and see if we can identify what material the ball bearing is made out of. This is actually a technique used to figure out what material something is made out of. Okay, and on your worksheet and here you have the formula for calculating the comparative specific heat within a calorimeter and a chart of common specific heat capacities. If you get something that does not meet your expectations, it could be one of two things. It could be it literally is not what you expected it to be, or of course it could be that these are not the most well-insulated calorimeters in the world. Like their top is only made of plastic. It's pretty easy for heat to escape. So if you get something ridiculous, then it may very well be just a problem with our lack of good experimental materials. Okay, good luck, have fun, be safe, gloves, goggles. Okay, I'll see you guys next academic week. Make sure that you turn in your little worksheet, and all right, take it easy.